Alright, so for this problem, a wedge, as shown below, is being used to lift a corner of a foundation of a house. I'm looking to cause an upward force of 1 ton, which is 2,000 pounds. I've got a coefficient of friction of 0.05 between the wedge and the base, and then the foundation piece and the wedge I've got a coefficient of friction of 0.15. So I want to know what's the pushing force required to get that 1 ton of upward force. So for this particular wedge problem, I'm going to go ahead and try and draw a free body diagram of the wedge itself and see if I can figure out what I need for this F push. So if I draw in my wedge, I've got a 10-degree angle right there. I'm looking to create a 1 ton upward force, which means that the foundation is going to be pushing down with 1 ton. I'm going to have the pushing force over here, and I'm going to have a normal force on the base like this. So this is going to be Fn. And I'm also going to have friction forces opposing this pushing force on both surfaces. So on the top, remember the coefficient of friction here on the top was 0.15. So 0.15 times the normal force being 2,000 pounds, that's my friction force. And it's again opposing the pushing force. So this is 0.15 times 2,000. Over here, I've got a second pushing force, or a second friction force. I don't know this Fn, but I do know that the coefficient of friction is going to be 0.05 times, the coefficient of friction is 0.05, so my friction force is 0.05 times that normal force. So this is 0.05 times Fn. So after I draw the ramp, I'm going to assume this body is in equilibrium. So I draw out my equilibrium equations. And I've only got 2 unknowns. I don't know the pushing force and I don't know this bottom Fn force. So I should be able to solve for both of those using sum of forces in the x, sum of forces in the y. So sum of forces in the x, I'm going to get 0.15 times 2,000. I've got a component of either of these. So my normal force is going to be the Fn normal force times the sine of 10 degrees. And I'm going to have the friction force, it's going to be the friction force 0.05 Fn times the cosine of 10 degrees. And then in the other direction, the negative x direction, I've got the pushing force. So minus F push. And that whole thing has to be in equilibrium, so the sum of the forces in the x direction has to be equal to 0. Now I move on to sum of forces in the y direction. So in the y direction, I'm going to have Fn times the cosine of 10 degrees. That's the vertical component of my normal force. I'm going to have negative 0.05 times Fn times the sine of 10 degrees. That's the downward component of my friction force here. And I'm going to have this negative 2,000 pounds. And I know the sum of forces in the y direction has to be equal to 0. So with all of this, I know that I want to solve for my pushing force. So to do that, I'm going to find my normal force first. So Fn, based on this bottom equation, the sum of forces in the y, is going to be equal to 2,000 divided by cosine of 10 degrees minus 0.05 sine of 10 degrees. And if I solve all that, I've just got numbers at this point. Fn will give me 2,048.9 pounds. And I can plug that into my top equation to solve for F push. F push is just going to be equal to 0.15 times 2,000 plus Fn, which is this 2048.9 times the sine of 10 degrees plus 0.05 times Fn, which is again my 2048.9 times the cosine of 10 degrees. And so all this long string of numbers, if I solve that out, I end up with, I require a pushing force equal to 756.7. So that's a fairly substantial force that's required to lift this house with a one-ton force. So I might want to find a different way of doing this. But with this, I've solved for what I'm looking for. So thank you for watching, and I hope to see you again.